is the function f of x is a rational if it's the quotient division to polynomial. P of x divided by Q of x. And both and P of x and Q of x are polynomial functions. We see several examples now. No restriction, any polynomial, arbitrary polynomial. However, the only restriction is that Q of x never is 0. Because you know what happens when you divide by 0, it's undefined. Okay, this is a definition of the rational division. Let's go to example. Wow. Example 1. Example 1 is f of x equal 1 over x. Wow, too easy. Okay, 1 is polynomial. Yes. 1 is just a constant, is polynomial, but degree 0. Because degree is the higher exponent in the independent variable que es x. In this case, you can interpret that 1 or 1 is like x to the 0 power. That is the reason that degree is 0. However, in the denominator, que es just x, x is to the 1 power, entonces the degree this is 1. There are no restrictions with the degree. In this case, we make it there and pray with the. Wow. Who make a noise? Okay. Let's continue. Putting off the microphone, please. You know, I put it off the microphone. I can control that. Oh, I put out the classroom. Okay. So the degree is the higher exponent. In this case, it's 1 and 0, but not all will happen. Let's see several examples I bring today. Okay. However, the most important thing is, okay, what is the factory for? Factory for. Factory, this is important. Factory for. Well, the factory for is when you are doing the factorization. In this case, it's impossible to do the factorization. To say 1 is 1 and x is x. To say no, we cannot do anything. In other example, yes, you see the modification and the domain of this elementary example is all real number except 0, because the restriction is, remember, when the denominator is not 0, so it's all real number except 0. You can write like that if you want. X such that x not 0. So in 0 we have a whole. Or not exactly whole. We have no whole. No, sorry, no whole. It's vertical asymptote. Look. It's a vertical. In 0 we have vertical asymptote. What is that? Well, I want to explain in detail now. Okay, suppose the graph look like that. This is the graph of our first example. I want to do by hand. However, if you want, let's do it now in decimals. I highly recommend using decimals in the test 3 and the test 4. Okay, the graph of the function, okay, by the way, is very well known. It's a reciprocal function. Look like that, similar to this. And we have one vertical asymptote at x equals 0. The representation vertical asymptote is a dotted line. But let me use another color. Maybe like that, blue color. Normally, I like black color. And I put the accent in black color. Okay, this is the vertical line, vertical dotted line. This is a vertical asymptote at x equals 0, because 0 in the denominator to be undefined. Okay, there are different behaviors of the asymptote. I want to explain. This is just the first example, guy. Don't ask me some question. You try to, I want to present any possibility we have. And after, I want to make conclusion about the, okay, about what? About the rational function, degree, in any example, factory form, domain, and verticast. Approximately the graph. Approximately the graph. Okay, let's move on to the second example, that is more interesting. Example 2. In example 2, the function is given is 5x divided by x squared minus 8x plus 12. Ooh, it's a polynomial on the top, degree 1. Because the exponent here is invisible 1. And again, it's polynomial at the bottom with the degree is 2. Remember, definition degree is the higher exponent that we have in the polynomial, no? Okay. Okay. What about factor 4? Well, the factor 4 is trying to do the factorization. So factor 4 is, well, in the top, we have monomial expression. Those say no factor 4 stays the same. However, here, yes, it's a trinomial. And we have the variable is x, and the combination in that case is 6 and 2, because 6 times 2 is 12, and somehow 6 plus 2 is 8, and negative both. This is the factor 4. Now, looking the factorization, I can see that the domain is all real number except the restriction, and the restriction is when there is 0, the denominator part. We have two factors. You copy separately x minus 6, no 0, x minus 2, no 0, therefore x no 6, and x no 2. The domain is all real number except 6 and 2. It doesn't matter the order, but it's both. You connect them by and. See, at least one is equal to 6 or equal to, we are undefined. Because suppose get 6 here, 6 minus 6 is 0, 0 times something is 0, and undefined. The answer is undefined, undefined. Remember, I repeat again the idea for the domain. Domain is the set of x value such that the function is defined. And the opposite idea for the defined is undefined. Undefined is that we have no value. Okay? Therefore, it's completely out the domain. So one easy way, well, no, you know this in the chapter 2, is you take the polynomial or the expression in the denominator bottom part, you enforce it to be equal to 0, and you solve this equation. In this case, we have the solution get 6 and negative 6. What about the vertical asymptote? Well, the vertical asymptote is associated with the restriction. In this case, I want to do approximately, no accuracy, the graph of the function. We have two vertical asymptotes, n, 2, and 5. Suppose it is 1, 2, 3, 4, 5, 6. We have another vertical asymptote. This is vertical asymptote 6. This is vertical asymptote 2. And my graph, I have no idea. I want to explain the technique to do the graph by hand. Look like that. Okay, this is in red color, is the graph of this original function. One super fantastic way to do that is using Desmos. I want to explain in a few minutes when I finish the introductory example. We have 4 introductory examples. Example 1, example 2, example 3, and example 4. After we discussing in detail another example. This is introduction. This is just the beginning. Okay, everyone follow me? So the thing I want to understand, degree, factor 4, domain, vertical asymptote. This is vertical asymptote. Vertical asymptote. The thing I put in blue color, vertical asymptote number 1, vertical asymptote number 2. This is at x equal 2, and this is at x equal 6. Super. Everyone follow me? Or totally lost? Okay. I want to complicate a little bit. Another weird example, or typical, or not typical. Example 3. Example 3 is, suppose the function is, I want to call g is equal x plus 3 divided by x squared plus 4. Okay, let me try. And the professor say que the factory form is when you factorization the polynomial, no? Of the top and the bottom. Well, by the way, degree here is 1 and degree of this polynomial is 2. Not necessarily always the degree of the bottom is bigger than. No. It's completely free. Then the factory form, it's obvious in the top we cannot do anything. And this binomial stay the same. However, this also stay the same because I know in intermediate algebra que the differences of the square is possible factorization like that. However, the sum of the square is prime expression. We cannot factorize. This is impossible to factorize. Another point of view. You see, when a professor say, you say it's prime, but why? Why is prime? Okay. See, for example, you enforce the situation. I want to investigate if we have or no vertical asymptote. Okay, you know, professor, okay, it's the line in which the function is undefined. You take the polynomial in the bottom and you enforce it to be 0. And you try to solve this equation. Okay, let's do it because I am expert doing this. In the chapter 1, we are doing a lot of quadratic equations. I feel strong in this. So x squared is equal to minus 4. I move 4 to the right hand side. You apply square root both sides. This is a square root method. And this is plus or minus 2i. Wow, look at that. When you try to find something in algebra and you get complex number or imaginary, it's because do not exist. Because this guy, you planning living in another field, not in the real field. I don't care complex field or imaginary field. I care only real field in this chapter. Entonces now, what is the domain? O sea, domain, remember by definition is all real number except the restriction. However, the restriction I try to looking for is imaginary, do not exist. So we have no restriction, and the domain in this is all real. Therefore, we have no vertical asymptote. So vertical asymptote, no. We have no. In this specific example, it was impossible factorization of the denominator. Okay? And you need to be aware for that possibility. The majority of the case, yes, it's possible, but sometimes no, it's impossible. Let me try another last example. So immediately when we finish and you a little bit understand, I want to show you the graph of this function in Desmos. Erase the board. Okay, example 4 gets very interesting. It's the last one, introductory example. Suppose the function I want to call p is an a, and this is the division 2 polynomial, x squared minus 5x plus 6 at the top, and x squared minus 7x plus 12 in the bottom. The degree is 2 in the top, and the degree is also 2 in the bottom. Maybe in this moment you don't understand very well what represent that, but I promise in one moment I explain. No, now I explain what the transcendental idea of the degree and what happened when the degree in the top is bigger than the degree in the bottom. But no now. Okay, let's move on to the factory form. Okay, it's the first thing you should do. factorization, the polynomial in the top, and factorization, the polynomial in the bottom. Two trinomials, xx, xx. The combination in the top is 3 and 2, I guess so. Because 3 times 2 is 6, 3 plus 2 is 5, negative both. The combination in the second is 4 and 3, no? 4 because 4 times 3 is 12, and somehow 4 plus 3 is 7, negative both. Okay, entonces en this particular example, I can see que one factor is cancelled out. So my factor 4 is now x minus 2 and x minus 4 can stay alive. However, what is the implication of the domain and the asymptote in this case? Okay, so you don't know anything at the beginning. You factorization the polynomial. Si we have a common factor, you cancel out. Si no common factor, no. Okay, no problema. Pero si hay common factor, you cancel out. Entonces, what is the interpretation of the factor gets canceled out? When the factor gets canceled out, is considered a whole. So we have a whole at x equal 3, no? Yes, the value of 3 make 3 here, 3 minus 3 is 0, 3 minus 3 is 0, a whole. And the representation for the whole, you know, you see before, is something like that. This is a curve, and we have a whole. It's a circle, a small circle, but it's completely open, no? And however, we have vertical asymptote only at x equals 4, que es de facto que stay alive in the denominator. Represent that. Okay, professor. Okay. And what about domain? Well, domain is both. Because in both a scenario, in 3 and 4, the function is undefined. Therefore, the domain is all real number is the x value such that that symbol, no 3 and no 4. But different reason, no? This is because it's a whole. Yeah, I understand it's a whole because it's the factor that is eliminated in the division, and this is no. This is stay and this is the asymptote. The vertical asymptote. Okay. Entonces, bueno, professor, entonces, definitely this expression, get the original you give me in the test, and this expression are 100% equivalent, is the same? The answer is no. Let me explain it. So this expression is the original, and this expression, okay, after the simplification, this is equivalent, I suppose, que 99%, 99.999%. That this, the true statement, the super true statement is this expression is the original, is given. Is equal this expression. But one condition, and when the x is not 3. Because in 3 we have a whole. This statement is completed true 100%. In conclusion. Not always happy, but sometimes happy. You express the new factory form. And the factory form, maybe yes, maybe no, some factors delete. And you get the new one. Reduce it in lowest term. And this is equivalent 100% the original? No. Because I eliminate the whole. Okay? And stay only in the 0 of the denominators you want. What is the formula for finding the vertical asymptote? Well, okay. You take the remainder expression in the denominator and you force it to be 0 and solve this equation. And in 4, we have a vertical asymptote. End of story. Okay. You have some question or no? I promise. And when you see decimal now, you see more clear everything. You see more clear everything. However, it's open to ask me any question, no? But let me try to open, first of all, decimals. Let me see. Oh, no. Oh, no. Sorry. Okay. In that window, I suppose. Okay. There you go. I see. Switching to decimals. Okay. Okay. Do you see that? Do you see decimal? Everyone saw decimals? Decimal. Okay. I don't want any student, my student, doing graphic by hand. No. You are doing using this fantastic graphic calculator free online. And you, in the test, you send me the picture of the graphic. How you create a picture. Let's move on to example 1. Example 1 is the first example we studied in the whiteboard. It's y equal 1 over x. And when you graph it that, boom, do you see this is the classical reciprocal function that we study in the library of this. But the important thing is, look, we have here one vertical asymptote at x equals 0, and you represent. It's important to say that the vertical asymptote is like a hypothetical line. That the curve, with the blue part is my function. The important part is the blue part. Approach it, but never touch the vertical asymptote. Never touch. So the distance, let me make it zoom. The distance between the asymptote, the vertical asymptote, and the function, decreasing, but never touch. Never touch. So to make it zoom, the original zoom, you click here in the house, bang, and this is the original. Do you understand this or no? Sure? Come on, guys, answer me. Feedback, participation, come on. I want to hear something. Yes. Okay, good. Oh, no, I don't know, zoom up. I am happy, I understand. Okay, participant, okay. I have a guess. Who is the guest? 16113 BC. Es de somebody got invited. I don't know. Well, okay, I don't care. Let's continue with the decimal part. Mason left. Mason. Okay, let's move on to the second example. Second example is, okay, this was the first one. The second, boom. Look at that. The second is, the function is 5x in the numerator divided by x squared minus 3x plus 12. In this case, we're discussing that we have two vertical asymptotes at x equal to, look, I'm flashing that, look, and x equals 6. Do you see? Where come from this? Of the factorization, that polynomial, well, the polynomial in the bottom. I don't know how highlight only this. Yes, I did that. Equal to 0, and when you solve in this quadratic equation, you get the vertical asymptote. Okay? We have more thing. This is complicated, guys. Rational function is very complicated. This is just the beginning. Okay, let me see the third example. Okay, it's very interesting. We have no vertical asymptote. We discover because the polynomial in the bottom give me imaginary solution. And so that means, well, the professor say, I don't know if it's true or false, that we have no asymptote. Let me try to do the graph. Look at that. No asymptote. Look. No, it's a smooth curve. No jump discontinuous. Okay. I understand now. And finally, the famous example 4, okay, we have a hole and we have the asymptote. Let me see how it look like. Well, it look like that. Boom. Okay. This is the original. Look, this is the original. Okay, I put in green color the curve. Okay, this curve I investigate. We have asymptote here. Look, N4. Que es the factor que stay alive after the simplification. But N3, we have a hole. Look at that. Do you see a hole? Let me make it zoom. This is the hole. And the hole is located in 3,1. By curiosity, I want to do the graph of the, this is the graph of the original. Boom. And the graph of the, after the simplification and the lowest term is this. Boom. Look like similar. Look, the blue and the green. What is the differences? The difference is that the blue don't contain hole because the hole belongs to the green. Okay? Do you see much better now? You see more clear now? Clear or not clear? Come on, come on. I am back. Skype. Shoot down on me. Okay. Okay. A ver, who is that? You are Clifford. Okay. Okay. Any question, guy? Do you follow me? Look like hard, complicated? No? Easy? Piece okay? Piece of rock? Opinion. Roy, opinion. Come on, activate the microphone or using the chat. Professor, I understand very well everything. Oh no, Professor, I am totally lost. Okay, let me study now in detail the vertical axis. Exactly, I say we have different behaviors and how you determine that behaviors. Okay. Do you see the whiteboard now or not yet? Let me see. Let me check it out. See, I share the screen or not. Switching to whiteboard. Boom. I suppose you see, right? Okay. We have 4 behaviors for the vertical asymptote. I want to study now. Look. 1, 2, 3, and 4. Suppose in every case, we have here 1 vertical asymptote. At a specific one point, I don't know, suppose x equal to arbitrary 2. We put the arbitrary number. However, the behavior can change, like that, for example. Suppose que one function, the graph will look like that. Another function, the graph will look like that. Another function, the graph will look like that. Another function, the graph will look like that. How do you know that? Easy. For example, I know que Fn2 is undefined in any case. That is the reason que it's asymptote. However, you evaluate, let me use this convenience notation. Evaluate in 2 plus. What means 2 plus? 2 plus is no positive 2. Is 2 plus is one number bigger than 2, pero close to 2. For example, 2.001 is 2 plus. 2.00002. So it's one number. I take complete arbitrary number here. This is 2 plus. Close to 2, but not exactly 2. Pero in the right direction. However, f and 2 minus is in the left direction here. 2 minus. Don't confuse it. It's no minus 2. It's 2 plus. 2 minus. And this minus indicate left. And the 2 plus indicate right. In both cases, in this example, 2 is positive. However, For example, si you don't like this notation, no problema, guys. You, for example, some people say, no, professor, I don't understand this notation. This is typical of the calculus. So you evaluate at 3, que is a little bit after 2 here, and you get negative value. I don't care the value. And you evaluate N1, que is a little bit before 2, and you get positive value. Oh, I know that the behavior is like that. Behavior number 1, behavior number 1. So I have some idea how it look like my vertical asymptote. Well, let's do exactly the same here, 3 and 1. But in this case, F evaluating 3 is positive, and F evaluating 1 is positive. So I know that the behavior look like that. Behavior 2. In this case, F and 3 is here. A positive value. F and 1 is negative value. Entonces now es behavior 3. And finally, si both are negative, and 3 is negative value. Look, negative value. I don't know exactly what. And 1 is also negative. It's behavior 4. The one fantastic way to have some roughly idea how to like the behavior of the vertical asymptote is after when you find the vertical asymptote position, you evaluate a little bit after and a little bit before, and you analyze the sign. Si es minus in the right and positive in the left, es behavior 1. Si es positive off, behavior 2. Si es positive in the right and negative in the left, behavior 3. And si es negative off, behavior 4. End of story. That's it. No big deal. Super easy. Any question? Guys, I suppose you have no complaint because I explain the complicated thing in easy way. Yes or no?
Can you repeat that one more time?
Yeah, what part?
The last thing you said.
Exactly. Okay. Mr. Holmes, you in that moment you determine the position of the vertical asymptote, okay, is at 2. I put hypothetical. Let's see in the actual example another number, no? But we have 4 kinds of behavior. Okay? Entonces now to determine what behavior we have in our specific example, you evaluate a little bit after 2 and a little bit before. And you analyze the sign. And you see both are positive or both are negative or alternative. One is positive, one is negative, and the right is positive and the left is negative. And you have the behavior. Clear? More clear? Don't try to find any missing confusion. No, it's straightforward. Straightforward. The thing you imagine is the idea. No, another thing. Let's move on to a no introductory examples, the actual example. I bring two. Example 1 and example 2. Example 1 is, well, f of x is equal to over x minus 3. Okay, and what do you want to find? Well, you want to find everything. You want to find domain. You want to find vertical asymptote. You want to find behavior of the vertical asymptote. Let's do it. Okay, the factor form. Well, by the way, the degree of this is 0 because we have no x. And the degree of this is 1. Okay, it's equivalent to say this is a linear, like a line. Okay, now the factory form stays the same. Because unfortunately 2 is 2 and x minus 3 is a binomial that is prime. We cannot do anything. However, I can see that now the idea behind the vertical asymptote is you take the expression in the bottom, that is x minus 3, and you enforce it to be 0. That say some people Some students say, Professor, what is the formula? Well, the formula is, remember, P divided by Q. It's a rational function. Well, so you want to find the vertical asymptote, you take Q always. Q. No capital. Q of x equal to 0. In our specific example, Q is x minus 3. And you solve this elementary equation, x equal 3. And x equal 3, we have one vertical asymptote. Okay, so I put my rectangular coordinate system. I want to see in decimal now. I want to show you in decimal now. Yeah, I know. Okay, at 3, 1, 2, 3, we have a vertical asymptote. Okay. And what about the behavior? No, I have no idea. I try to investigate. How you investigate? Well, you investigate, see, this is x equal 3. Okay, it's my vertical asymptote. You evaluate. I know that the function evaluating 3 is undefined. That is a reason that is vertical asymptote. However, you evaluate in 2 and 4. 2 and 4. Entonces, plug in where? In the original equation, this one. Entonces, 2 over 2 minus 3. Plugging in, replace x for 2. 2 over negative 1 and negative 2. Wow, and negative. And negative 2, y value. This is a y value. This is x value. 2 comma negative 2. I suppose that here. Negative 1, negative 2. That point. That point is the point, 2 comma negative 2. And 4, exactly the same. 4 minus 3. 2 over 4 minus 3 is 1, is positive 2. The y value. So it's 4 comma positive 2, is 1, 2 here. This point. So I suppose, using my common sense, in my imagination, can my curve look like that? I have not too much information of the rest of the point, but I know that the behavior look like that. That's clear? And what about domain? Well, domain is all real number except the bad guy. Who is the bad guy? The bad guy is 3, case in which you have the vertical asymptote. So you represent like that, x such that x not 3. Make sense because 3 minus 3 is 0, division by 0 is undefined. You know what is the reason is undefined. Super clear. Any question? Any question? Any question? Any question? Let's move on to the second example. No? No? Guys, everything is okay or no?
Everything.
Okay. This is the thing I want to hear. Oh, question. I don't. I like you ask me a question, no? Of course, a smart question, no? What is the stupid question? The stupid question is I don't understand anything. So you don't give me information. What part you understand and what part you don't understand. Now anything is I don't pay attention, maybe, no? Let's move on to the second example. Second example. I want to erase the board now. Second example is a little bit more interesting. Example 2 now is, look, g is the name of the function. In this case is x minus 3 in the top over x squared minus 5x plus 6 in the bottom. Okay, the analysis of the degree is 1 of the top and degree is 2 in the bottom. Easy. Okay. And what about factory 4? Factory 4, in the top we cannot do anything, unfortunately, but on the bottom, yes. A factorization this, the combination is obvious 3 and 2, because 3 times 2 is 6 and 3 plus 2 is 5. Negative both. Yeah, I can see, wow, look at that. One factor is cancelled out. Chum, chum. And my factory form look like in lowest term like that, x minus 2. So what is the conclusion? When the one factor is cancelled out, it's gone, it's because we have a hole. So we have a hole at x equal 3. And we have a vertical asymptote at x equal 2. So you take the polynomial, the remaining polynomial, so the rest can stay alive after the cancellation. I copy, x minus 2 equals 0. And so for x is 2. And at x equal 2, we have vertical asymptote. Okay? Okay. And what about domain? Well, domain is, let me see what domain. Domain is all real number except the bad guy. Who is the bad guy? Well, both, a whole and 2. Okay, because we are talking about domain of G, que es the original. This is equivalent 100, not 100%, you know, some percentage. Let me call G prime. No, no prime. No, another name. H prime. H. No prime. No prime. Because prime in mathematics is another thing. H. H and G are similar, except that H have no hole, only vertical asymptote, and G have both. Therefore, the domain is no 3 and no 2. The reason is clear. In 3 we have hole, and 2 we have vertical asymptote. So let's try to do our best doing the graph by hand without decimals of this graph. Let me try to do my best. Something like that. X1. Well, I know. In 3, 1, 2, 3, we have vertical asymptote. That is the reason I draw dotted vertical line. This is the vertical asymptote at x equal 3. But entonces I need to investigate behavior. I need, no, in 2, sorry. I make a mistake. It's in 2. It's in 2, mistake. It's in 2. In 2 is a vertical. Yes. Here, over there. Vertical asymptote at x equal to. In 3, no. In 3 we have a hole. So I propose you evaluate, in order to determine the behavior, you evaluate, well, in 3 I cannot evaluate, because I know this is 2 and this is 3. I know que si yo evaluate en 3, G is undefined. Okay, pero where is second? Because in 3 is a whole, pero we can evaluate in H3. Entonces en 3 we have in H, que es that expression, is 1 over 3 minus 2. 1 over 1, que es 1. Entonces 3,1, pero 3,1 is a point to this, to H, que es equivalent a hole. So we have a hole here. It's undefined. Okay, entonces I suppose using my imagination, well, no imagination. Entonces, in 3 is not good to evaluate. Let me evaluate in 4. Remember, totally arbitrary point after the vertical asymptote in order to determine the behavior. Suppose G and 4. Okay, G and 4 is 4 minus 3 divided by 4 squared minus 5 times 4 plus 6. Okay, by the way, is equivalent to evaluate here. 1 over 4 minus 2, because these and these are equivalent except in a whole. But in this case, Caesar, the mathematical operation is 1/2. So say 1/2 and 1/2, I suppose. Positive 1/2, point is positive 1/2. So say, I know. Okay, my curve, approximately, using my common sense and my imagination, is here. We have a hole here. This point is I don't know exactly what happened in the last part. It's not important now. I explain another thing, today, next lecture, to continue this. But important is that the curve approaches to the vertical asymptote, but never touch. Okay? And what about the left part? The left part, I propose to evaluate GN1. GN1, o en 0, o en -1, any arbitrary value. Entonces, well, es 1 minus, let me see, the original is, there you go, is 1 minus 3, or minus plus 6, pero more comfortable doing in this, que es 1 minus 2, que es -1. Entonces 1 over -1 es -1. Wow, es -1. Entonces en 1 es -1, en y value is here. Okay, this is my point. Entonces I suppose, using my common sense and imagination, que the curve approaches to the asymptote, never touch, in this case passing through that point. I have no clear idea what happened here. But the important thing for me now is the vertical asymptote, the hole, and the domain. It's the important thing now, right now. After we have more characteristic of the rational function I want to study. Now let me see. Yeah, we have time. Any questions so far? These two more interesting examples. Let me show you. Go ahead, Clifford.
Can you go over the h of x again? I mean, not the h of x, the h of 3. I got lost there. I'm not sure why.
What part you want? Go again.
Lost h of 3. Why h of 3 instead of, like, why is it different than g of 3?
Okay. Your point is what is the difference in 3? What's going on
H of 3 and G of 3. You know how to say
Okay, I got it. Okay, G and 3 for sure is undefined. Let me explain why. Because G and 3 is 3 minus 3. I plug it in here. 3 squared minus 5 times 3 plus 6. And the top is 0, but I don't care. The top is not important. And the bottom is 9 minus 15 plus 6. Entonces 9 and 6 is positive 15 and minus 15 is 0. 0 over 0. And the thing that we are doing to this simplification, cancel out x minus 3, is cancel out this. We cannot do anything. This is valid. This simplification is valid when the x is not 3. Or the y, yes. But in 3, no. So the interpretation of this is a whole. And the representation graphically in 2 dimensions is like that. At that point, 3, we have no y value. Well, entonces you say, well, but what is the reason that you locate in 1? Well, because when you evaluate h in 3, okay, h is this expression. The answer is 1 over 3 minus 2 is 1. Okay, entonces now I know that my curve is, is continuous. However, in the whole, we have discontinuous. Do you understand what is the difference between G and H? H is the equivalent, but not 100% the original, because you simplification the common factors in the top and the bottom. This statement is valid for the value que is no 0, because 0 divided by 0 You cannot divide 0 divided by 0. 0 divided by 0 is undefined, and any number divided by 0 is also undefined. This is two reasons. Actually, this is undefined. In calculus, if you take calculus, this is called undeterminate. But it's in algebra, it's the same. In calculus, no. In calculus, there are a little bit subtle differences. Do you get the idea or no? No? Not yet? Okay, super. Okay, let's move on to the next topic. That we studied today. The next topic, no. It's the same topic, but it's another characteristic of the rational. It's called horizontal. Horizontal asymptote. So we studied vertical asymptote. Now we study horizontal asymptote. First of all, definition. What about? Okay, wait, let me try to understand horizontal asymptote. We have different behavior for the horizontal. Horizontal is a horizontal line. So, for example, you have that situation. X, Y. Okay, good. Okay, horizontal asymptote. Suppose que look like that. Pam, 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 pam. Horizontal. Maybe like that. Okay, again happen que approach pero never touch. Suppose, this is one possibility. Another possibility is when we have this. Okay, y one possibility is you cross it. Here, you cross it. You cross the horizontal asymptote. Okay, this is not always happen, but sometimes happen. I want to explain in detail, but in your moment, not now. Okay, so let me try to understand what is the horizontal, what means horizontal asymptote. Well, horizontal asymptote is equivalent to say M behavior. An A behavior is a quantity, the Y value, when the X approaches to infinity. That is the reason it's N behavior in the infinity or negative infinity. Okay, to be positive infinity or negative infinity, infinity is no number, infinity is a symbol that indicates us a huge number positive or a huge number negative. And you see here, let me try to see in the first graph, in the first one, okay, when the X approaches to infinity, look, X approaches to infinity positive. In that direction, our curve, okay, the curve is the red color, approaches to the asymptote pero never touch. And likewise, when the X approaches to negative infinity in the opposite direction, it's a negative infinity, X approaches to negative infinity, the curve also approaches pero never touch. Okay, the 99% of the case never touch. 100% like that touch, cross. But don't worry for this right now. So how you know? How do you know? Okay, how you find the horizontal asymptote? Because professor, you explain me vertical. I understand very well vertical, but horizontal, I have no idea. Okay. Let me explain. We have two scenarios. Let me explain now horizontal asymptote, a scenario. Horizontal asymptote, horizontal L. I forgot the L. Asymptote. Okay, this is the regular case. Okay, the case that most often occur. And we have one special. Okay, But I want to talking about regular case now. This situation happens when the degree of the polynomial in the top, okay, this situation happens if degree of P is equal degree of Q. I want to call the analysis of the degree. So to determine horizontal asymptote, we need to analyze degree. Suppose, example to understand, one example. Suppose a function like that, g of x is equal to 7x squared plus 2x over 4x squared minus 3. Okay. The professor gave me this rational function, and the question say, we have or we have no horizontal asymptote. And okay. I saw that the degree of this polynomial is 2. And the degree of this polynomial is also 2. And the professor say that when the degree is the same, we have. So the conclusion is we have horizontal asymptote. But I want to explain more. I want to explain why. I want to explain at what value of this. The idea is clear, guys. X approaches to infinity. You suppose in your mind a huge number, 1 million, 1 trillion. This is infinity positive or negative in both scenarios, positive or negative. Entonces, when you plug in one huge number here, when you plug in one huge number here, we have 7 times infinity squared plus 2 times infinity. Wow, what the hell is that? 4 times infinity squared minus 3. I anticipate you that we cannot do any arithmetic operation using infinity because infinity is no number. And infinity give me unexpected answer, okay? So now, the thing you need to understand is completely different. You need to understand. Infinity squared is bigger than infinity. Infinity squared is bigger than 3. 3 is just $3. And infinity is 1 trillion, 1 million. And this is 2 times, so when you increase in the exponent, this is the dominant term. Dominant term. In conclusion, you take only the leading coefficient in the dominant term, and the rest is completely negligible. I cross in my mind. Because the dominant, so the substantial value is always the higher exponent. You take the higher exponent in the top, you take the higher exponent in the bottom, but in this case, by coincidence, it's the same, it's 2. Therefore, my A behavior of G is just 7x squared over 4x squared. And you cancel out x squared, and the answer is 7 over 4. And this is my horizontal asymptote. Okay. Y equals 7 over 4 represent the horizontal asymptote. Entonces, conclusion. Es easy, no complicated. When the degree is the same, that means that both polynomials increasing in the same speed, in the same rate of change. Therefore, you take the dominant term, you delete mentally the lower exponent, 1, 0, and you take the higher exponent. And the coefficients in front, okay, 7 and 4, represent the horizontal asymptote. This is a regular case. We have no time to explain the special. But I left two examples. Okay, I encourage you. Can you try to investigate see we have or no vertical asymptote? Suppose this ax squared plus 9x minus 5 divided by 2x squared plus 1. And this function I want to call h. And we have another. Okay, is p. And p is x squared plus 7 over 11 minus x squared. I have two questions in both examples. Question number one. Horizontal asymptote exists or no? And the second question is, at what value? At what value? What do you think? In the first example, we have or we have no? Yes or no? It's easy. It's yes or no question. Yes or no?
Yes, yes.
The answer is yes. Super. What is the reason? The reason is because the degree of the polynomial in the top is 2. And the degree of the polynomial in the bottom is 2. And the professor say that always that this is happening, we have horizontals. And my question is, at what value? At what value?
What
y
is
equals
it?
something? Eh?
8 over 2.
A over 2. A over 2 is 4. And y equals 4. Okay, super. This is the idea. This is the idea. Who helped me in the second one? Same question. We have yes or no? Question 1. Yes, no.
Yes. Yes.
Yes. Why? Why? What is the degree of the polynomial at the top?
2.
2. What is the degree of the polynomial at the bottom?
2.
2. I put it to confuse you in different order, but it's 2. It's the higher exponent, right? So my question is, and what is the at what value is the horizontal asymptote? At what value? Y equals something. Y equals something. Y equals something. What is the dominant? Go ahead. Go ahead. Come on, go ahead, answer me. What is the value of the horizontal asymptote? Remember, what is the dominant? What is the dominant term? This is the dominant. Look, and this is the dominant. No? I put in different order to confuse you, because I need to train you to see that. So you keep only the dominant. 7 and 11 is nothing.
No.
It's nothing. Because in my mind, x is a huge number. Therefore, is the coefficient here is 1. Well, no, actually, it's x squared over minus x. Yes or no? It's negative 1. Boom. Final answer. Okay, so we continue next time. Next time, we continue the analysis of the horizontal asymptote and another asymptote that we have. We have 3 kinds of asymptote. Vertical, we studied today completely. Horizontal, we start, but we don't finish because you have a special case. And we have another asymptote is slang. And finally, we integrate everything, 3 asymptotes, 3 kinds of asymptote. We'll be able to identification, see exists, no exist, at what value, and integration with another point, like a y in a set, x in a set. Entonces, I explain 7 steps to make a graphic for the rational function, and always we are using Desmos guide, never by hand. Okay, any question? Any question? Any question? Remember, we have lecture this Thursday, and we have tutoring the student can eat this Friday. Super?
Yes.
Okay.